Think like Tesla.
Welcome to Think Like Tesla. My name is Micah, and today we get to try something I've always wanted to try. Okay, so around about the 19th century, people figured out if you have a wire and you have an electric current, if you have moving charges flowing through the wire, it will create a magnetic field at a right angle to the direction that the charges are moving. All right, so if this wire here had a current flowing through it, we can visualize it like this. The magnetic field is circling the wire like this, while the charges are, according to this arrow, going that way. So the magnetic field is just circling this wire whenever there is a current moving through the wire. That's pretty cool. Now if you take the wire and you curl it into a loop, all these magnetic charges circling the same way all end up pointing through the loop one way or another, and that strengthens it. That's why we see a lot of looped wires in electromagnets and inductors and such. Okay, so this is called the right-hand rule, or the right-hand curl rule, meaning if you make this shape with your hand, with your right hand, the curl of your fingers, if that's the direction the current is going through the coil, the direction your thumb is pointing is the direction of the magnetic field. It works the other way too. So if your thumb points in the direction that the current is flowing, your fingers indicate the direction that the magnetic field will be curling. I only have two questions about the right-hand rule though. One, what do you mean by direction of a magnetic field? And two, what do you mean by direction of current flow? Let's talk about current first. So, the diagram you've seen before on this channel, this one right here, showing an LED, is a load in a circuit. So the positive side of the battery, the longer line, it looks like if you follow the arrow, looks like if the current is coming out of the positive side, it follows the arrow and goes through the circuit. That's called conventional current. What we actually know, though, is that this is electrons flowing. Electrons are going to flow in the opposite direction through the circuit, and that's called, well, there's different names for it. Also, magnets. Permanent magnet has two poles. We call these north and south. As you can see here, typically the north pole has an N on it and is typically colored red, south blue. So I can stick these onto my wand here, and I can influence a compass. Now the iPhone, curiously enough, here seems fairly shielded against this kind of interference. But here's the thing I always wanted to try. We're going to make a really sensitive instrument here by taking a cork with a needle. I've run the magnet along the needle here to magnetize it, and there's a little drop of nail polish on here to hold it on. So if we float that in water, it should end up pointing more or less north, if it doesn't bump against the side of the container too much. And then the other thing we have here is a handmade electromagnet. So this is about 13 millihenries as it measures out. It's a spool wound around many times with turns of magnet wire, and the inside is filled with soft pieces of iron. This is actually a cut-up coat hanger. So we can experimentally verify what happens here. We can verify the right-hand rule. Okay, so I'm going to apply a voltage to it. This is current limited to about 0.5 amp. Okay, now you notice when this happened, the compass is attracting the south pole of this magnet. So what do we mean by south pole? Well, it would probably be more accurate to call it the south-seeking pole, right? So the north pole of a magnet, if you suspend it by a string here, it is going to try to orient itself towards pointing north. Of course, there's lots of interference and other things on this desk here with all these circuits running, but the north pole of a magnet is going to point more or less towards compass north. So that means actually the magnetic field closest to the north pole of the Earth is actually the magnetic south pole. So that's kind of weird. Okay, but anyway, so you can see on this coil here, it's definitely attracting the south pole here. The coil is wound in this direction. So in my right-hand rule, I'd have to flex my hand like this with my thumb pointing down into my desk. Illustrated, it would look like this. Okay, so notice we got the plus wire on this side, the minus wire on this side, the curl goes that way, and you see the magnetic north pole is showing up on the top here, and the south pole here. That's why the south pole of these magnets are attracted to it. And we can verify that if we reverse here. I'm going to take these wires off and reverse them. If we hook it up this way, that guy flips around so that the pointy end is now pointing at it. But let's put it back. Okay, so what can we figure out from this? So the right-hand rule, as commonly stated, applies to the conventional current flow. So if we look at the plus wire going this way, we would actually curl my fingers this way with my thumb pointing up into the camera. That's the right-hand rule, and it's producing a north magnetic field on the top here. So this video is out here for my benefit as much as anyone else's. If I ever need to remember it, I have something to go back to, and that's how that works.
Teslanomicon.
Today's reading recommendation is the ARRL Handbook. This is a truly massive book. It is just thick and dense and crammed with every kind of information relating to radio, antennas, general electronics, assembly, circuit boards, you name it. So this comes out every year. This is the 2018 edition I have here. You do not need to rebuy it every year. You get one, you are good for decades, if not a lifetime. So if you're into radio, if that's of interest to you, treat yourself and pick up one of these. Links in the comments below. In a previous episode, I showed off my paper circuit concept here, even though it's on plastic, using conductive tape and conductive ink to attach this LED here. So some people are wondering, well, what kind of conductive ink did I use? Well, let me show you some of my experiments that I've got around conductive ink. So the one I actually used in that device I just showed was Buddy Paint Kit. It's like a ballpoint pen kind of thing. You shake it to make the ink get all mixed up. I will put a link to where I got this if I can still find it. Another one I tried was Bear Electric Paint. Got this at Maker Faire. And as to make the experiment fair, as a control, I tried Sharpie marker here. This blob of stuff is not designed as a conductive paint at all, but it is a peel-off face mask with bamboo charcoal. If it has charcoal in it, in theory, it should be conductive. And we also have a control here of pencil. So this is from a Blackwing Palomino pencil. So let's grab our ohm meter here and see what we got. All right, this is on relative resistance mode. So my lead resistance is all compensated for down to 0 here. Let's try the control first, the Sharpie marker. I'm going to push these are quite pointy leads, and I'm going to push them in there with some amount of force, and we're getting nothing. So Sharpie marker is not conductive at all. Neither is just plain paper. Okay, let's try the face mask material, the bamboo charcoal. Push that in there. Bamboo charcoal is also not conductive. Apparently they use filler materials and things in that prevent the carbon particles from touching each other and conducting. All right, let's try the Buddy paint, the gold stuff here. Push that on there, and we're getting about between 5 and 6 ohms, which is not too bad for a trace that size. Let's try the Bear conductive paint. This is definitely carbon-based. Push that on there. Getting about 32 ohms. So not as good as the metallic stuff. And let's try the pencil here. Now, pencil is supposed to be, graphite is supposed to be conductive, but I am not getting this to conduct at all. This is a sensitive ohm meter. It would register up to 40 megohms. So there you have it. If you're into making with conductive inks, try some of these out. If you have other things you would like to have seen in this experiment to see what their conductivity is, let me know in the comments. All right, thanks. Oh, and I almost forgot. In eBay and a lot of sites, you can get these little tiny containers of conductive ink. This is like half a milliliter or so, but it gets really dried. This smeary looking thing here is the conductive ink. The best I could get it to lay down on the paper. It's both too wet and to really make a good connection, and too dry to get out of the syringe in a reasonable way. But let's see if we can do anything with that. If I get it right on the gobs, the thick gobs here. So yeah, that's not very useful either.